Not. Welcome to the Monday seminar. My pleasure to run this again today. It's been going on for a while. This is a completely informal opportunity to get together across the world and to talk about earthquake physics and other things, sometimes machine learning topics. And because a good an organization of great people like Pierre Dublanchet, who has organized the talk for us today. Our normal mode of operation is to ask people to mute themselves during the talk, but to feel free to unmute and interrupt with points of clarification along the way. Pierre will probably give a talk that lasts something like 45 minutes or an hour, I'm not sure. And then we have about 30 minutes for questions and discussion of different sorts. So it's been one of the nice things about the online format is that, of course, some people will have to go before the end, but it means that we can devote a nice time for questions and discussion. So without anything further, I'm going to turn things over to Pierre and thank him for being here.
Okay, thank you, Chris, for organizing the seminar, for the invitation, and also thank you to all of you for being here today. So the work I'm going to present today largely results from a collaboration we have with Louis de Barros, Martin College, Gianluca Gerardi, and Frédéric Capa. And part of it is in the framework of a French A&R project called INSEIS. So the main focus of the presentation is about how to use earthquake catalogs to quantify faulting process at depth. So as an introduction, I would say that we know that different mechanisms can participate in the triggering and the development of earthquake sequences. The first one is tectonic stress accumulation along plate boundaries. So this here is an example from Iceland in the Tjørnes fracture zone, where you have lots of swarms driven by extensional tectonics. But we also know that large part of the natural seismic activity can also be driven by fluid overpressures at depth, either because of direct pore pressure changes on fault or through more complex thermoporoelastic stress redistribution.
Pierre,
So, yes.
sorry, the top of your screen is cut off by a little banner. Maybe if you click on your slides, it goes away. I don't know. Yes, now went away. Thank you.
It's going away. Okay.
Yeah.
Is that fine now? Yeah. Okay, good. Okay, so the participation of fluid is something that is suggested in part by the similarity between natural and induced earthquake swarms, especially in the migration patterns. So here you have an example on the left of a Bohemian earthquake swarm that shows this diffusive-like migration pattern. But it's also something that is suggested by the occurrence of seismicity modulation in response to hydrological load variations, such as in the Himalayan seismicity that is clearly seasonally modulated by the monsoon. Then we also know that many earthquake swarms are connected or triggered by aseismic slip events. Here is an example of the Salton Trough in California. So this swarm is associated with aseismic slip that in some cases can be detected and measured by geodesy. But generally for earthquake swarms, this is something that is not systematic. We also know that some earthquake swarms involve repeating earthquakes, which strongly suggest also the presence of aseismic slip. And then we also know that some swarms involve at the same time, tectonic stressing, aseismic slip, and fluid. And this gives rise to a very complex hydromechanical history. And the only thing that we can measure out of that generally is the earthquake activity. Now, in many active regions in the world, we nevertheless have a very detailed picture of the seismic activity. So we had recent advances in the treatment of seismological data, in the detection, in the location, and now it provides us huge high-resolution catalogs. So here I show you an example of the Corinth Rift in Greece, where we have over a period of 10 years, we have about tens of swarms per year with a total of a few thousands of events. So in this place, the earthquakes are essentially concentrated in a subhorizontal layer between 5 and 6 kilometers depth. And in this case, in the Corinth Rift, we know that the seismicity results at the same time from extensional tectonics, from fluid diffusion processes, and also possibly from aseismic slip. However, in this case, we would like to be able to quantify these processes, to quantify the volume of fluids involved, to quantify the amount of aseismic slip, and to be able to extract as much mechanical information as we can from the earthquake data. So here is another nice example. So this is the Alto Tiberina fault zone in the northern Apennines region of central Italy. So a catalog of more than 400,000 events has recently been established for this region. And this catalog shows a very rich behavior of earthquake activity on a well-documented fault network. So here again, you can see that, I mean, in this case, as in Corinth, the seismicity results from tectonics, from extensional tectonics, from fluids flow at depth, from aseismic slip, and we get a very complex earthquake swarm pattern with migration epizones and swarms at different scales. And here, as in Corinth, we have a great opportunity to study the physics of earthquake triggering. And here again, we want to have tools to quantify the faulting process at depth from the catalogs. So one way of studying these catalogs is to look at the statistical features. We know, for instance, that the earthquake magnitudes distribute according to a power law that is parameterized by the exponent B that we call the B value. So this is the Gutenberg-Richter law. We also know that aftershock rate decays as an inverse power law of time from the main shock following the Omori law. And we also observe robust scalings that relate seismic moment, earthquake duration, or recurrence times of repeating events. These scalings are generally empirical laws, and they are quite robust, but we observe at some point some variability in these distributions that raises the question of the mechanical origin of these different scalings. If I look, for instance, at the magnitude frequency distribution, the B value question is something that has motivated a lot of work. And in the case of natural earthquakes, for instance, we often interpret the B value changes observed with the differential stress that occurs on different faults. And this interpretation is generally consistent with observations done at the laboratory scales, where acoustic emission magnitude statistics is also controlled by the differential stress experienced by the sample. But we also have other observations, in particular in the case of induced seismicity, So here I show an example of the Groningen the Groningen induced seismicity, showing that the B value is also controlled by the stressing rate, the poroelastic stressing rate that occurs in the reservoir. So from these different scalings, it is still difficult to use the B value as something to quantify the stress on faults at depth or to quantify the stressing rate that is experienced by the different faults. Recently, the question of mechanical control on earthquake statistics has also greatly benefited from the study of induced seismicity clusters and from hydromechanical experiments performed at smaller scales. So in these cases, the faults are generally stimulated in a more controlled manner than what we can do with than what we observe in the case of natural earthquakes. And today, there are strong debates about what controls, for instance, the maximum magnitude or the earthquake migration speeds that we observe during fluid-induced earthquake swarms. So is it a question of total fluid volume involved? Is it a question of overpressure, of injected energy? But all these observations give some hope that earthquake statistics can also be used to quantify hydrological processes at depth. So if I make a summary of the situation, the current situation, we have now high-resolution earthquake catalogs. And to interpret them, we have, in the best case, semi-empirical scalings to interpret these catalogs. But still, we have some difficulties to quantify the stress at depth, to quantify the amount of seismic slip that is associated with the seismicity, and also to quantify the fluid overpressures. So one way to deal with that is one way to improve our understanding of how mechanics control the earthquake statistics. It's to use physics-based models that are able to generate sequences of earthquakes from a given hydromechanical loading. So generally, we call this class of models earthquake cycle models, and they are based on the coupling between elasticity, in some cases even thermoporoelasticity, and dynamic friction along a given fault network geometry. So there are different ways of constructing such models. So I will not make a review of them, but I will just illustrate some different approaches that have been used to model the faulting process. So one possibility is to model the fault population as a population of non-interacting spring and slider systems obeying rate and state friction and obeying common shear and normal stress histories. So this this approach is widely used in general to model the seismic activity in a reservoir following a fluid injection. So in the first step, the idea is to compute poroelastic stresses from a poroelastic model that would result from the injection into a reservoir, and then to extract the stresses from this modeling and to use it as a forcing of seismicity that can be computed from the Dietrich 94 model. So the use of rate and state friction in this case allows to have a spontaneous nucleation of earthquakes and also to have a realistic time-dependent fault response to a complex stressing history that comes from the poroelasticity. However, the problem with this approach is that it does not account for aseismic and seismic response at the same time, and it cannot also account for stress redistribution between the different earthquakes. And finally, there is no magnitude prediction. In this sense, it is also limited to have a better understanding on what controls the statistics of earthquakes. So there is an alternative approach that is often used is to consider the quasi-static equilibrium of a simple frictional planal fault that is experiencing poroelastic stressing. So this kind of model has been developed generally to understand the coupling between fluid overpressure and aseismic slip that is suspected to play a role in many fluid earthquake sequences, but also during hydromechanical that is observed during hydromechanical experiments. So the main outcome of this model is that for a given fluid overpressure, the magnitude of the aseismic slip is largely controlled by the initial state of stress that prevails on the fault, which can be quantified by a stress parameter ratio that is written here, that involves both initial stress, the frictional strength of the fault, which is the product of the friction coefficient F and the effective normal stress, and also by the overpressure that controls the fluid diffusion, the term delta P here. So the idea is that fault closer to failure can generally produce aseismic slip fronts that will propagate well beyond the pressurized region. So the nice thing with this approach is that it is generally possible to derive closed form solutions and to get theoretical scalings out of that. But here again, it focuses essentially on aseismic slip, and there are no earthquakes that are produced in this kind of model. So this is maybe not the most appropriate way to study what controls the earthquake statistics. So of course, the last approach, the previous approach, can be extended to account for more elaborate physics, including, for instance, rate and state friction, including complex geometry with fault roughness, or complex hydromechanical coupling, including dilatancy or nonlinear permeability laws. Here, there is a recent example of such an attempt with roughness, with rate and state friction, and also with complex hydromechanical coupling. And this way, you can see that we can retrieve a very rich variety of fault response to a fluid injection. So we have seismic events, we have aseismic slip that propagates along the faults. We have complex migration episodes. And again, the behavior that we see in this kind of model can partly be explained by the state of stress prevailing before the injection through a stress parameter T, just like in the previous approach. However, generally, this very advanced physical coupling is investigated using 2D models, which can be also problematic when we want to compute magnitudes. And also, the statistics of earthquakes are not generally not investigated in details. So in the following, I will report on an alternative approach that relies on what I would call a 3D asperity model. And this model is specifically dedicated to the study of the mechanical control on earthquake statistics. So an asperity model can be defined as a classical earthquake cycle model. So it still builds on a coupling between elasticity and rate and state friction. So here we simply consider a 2D planar frictional interface that is represented in gray. between finite elastic slabs of thickness h. So in this model, the fault slip is forced in the x direction by a constant tectonic rate, represented in green here, Vp. And eventually, we can also impose transient pore pressure changes that would arise from a point source of overpressure that is located within the fault. So to allow for both aseismic slip and spontaneous nucleation of earthquakes, the fault here obeys rate and state friction, but obeys heterogeneous rate and state friction. So we define a set, the idea is to define a set of asperities. So asperities here are frictional asperities. There are patches that are characterized by velocity weakening behavior. And these asperities are embedded into a velocity strengthening background that would respond to tectonic loading by aseismic slip. So here an important parameter is what I call the asperity density. This is the ratio between the velocity weakening fault surface and the total fault surface. Um, so here the asperities are simply drawn from power law distribution. So the size of the asperities is drawn from a power law distribution, and they are distributed on the fault plane with a possible overlap. And the other important thing is that we consider in these models that the critical slip for rate and state friction depends on the scale of the asperity so as to generate a scale-dependent fracture energy. Then we simply assume that a stress balance between the frictional strength, that is the product of the friction coefficient F, and the effective normal stress, which is the difference between sigma, the lithostatic stress, and P, the pore pressure experienced within the fault. And this frictional strength is balanced by the elastic stress, tau E. So the friction coefficient obeys rate and state friction. And the elastic stress is given by three contributions. So we assume here a quasi-static elastic framework. So the elastic stress is given by the background stress related to far field loading, plus a term incorporating the elastic stress redistribution within the fault. And finally, the radiation damping term here that allows to account for elastic wave radiation in an approximate manner. And finally, in case we have fluid injection, the pore pressure here is simply provided by a diffusive solution with a constant injection rate at the injection site. So here you have a pore pressure that evolves with distance from the borehole R, time t, and that involves the injection rate Q, the fluid viscosity eta F, the permeability KH, the fault thickness W, and you have the diffusivity alpha that is given by this expression with the compressibility of the fault C and the porosity phi. So
Pierre,
from these different, yeah.
Pierre, sorry, it's Chris. Just a quick point. So your fault is planar, but it has a finite permeability, and that is basically the result of kind of tortuosity around the asperities. Is there any physical significance of the finite permeability?
Well, the permeability is assumed here to be constant, so it's not related to the asperity distribution, to the tortuosity, or I mean, this is just a very simple
Yeah, I see.
a simple approach where the permeability is assumed to be constant. Yeah.
Okay. And the velocity weakening area is the area of the asperities.
Right. Right, exactly.
Gotcha. Thank
Yeah.
you.
Yeah, so from this set of equations, they can be solved numerically to extract the fault slip and stress history. And from this slip history, we can extract an earthquake catalog, assuming that an earthquake occurs each time the slip rate exceeds some radiative threshold that is of the order of 1 centimeter per second. Um, so more specifically, I will show some results that were, I will show earthquake catalogs that were obtained under 3 different fault scenarios. In the first one, we assume that we have seismogenic asperities represented with the white circles that are embedded in a fault that is experiencing continuous aseismic slip. So in this case, the aseismic slip occurs close to steady state, which means that the whole sequences, during the whole sequences, the aseismic slip rate remains close to the tectonic rate that is imposed in the far field. So this is the first case. In the second fault scenario, which I called locked dry, the background velocity strengthening region is contrary to the first case, is well below steady state, meaning that we still have aseismic slip in between asperities, but this aseismic slip is negligible, is very slow. So if you prefer, you can assume that the asperities are embedded in a quasi-locked environment. So these 2 first scenarios are dry in the sense that seismicity is only driven by tectonics and aseismic slip, or not. But there is no fluid overpressure within the fault. And then I have a third fault scenario, which is simply the first one, but with a fluid injection added on top of the tectonic loading. So in each scenario, I generated 25 asperity distributions, which all have different asperity densities. And I also try to explore different initial stress conditions on the asperities, but also different frictional properties on the background velocity strengthening regions. And finally, for the injection scenarios, I also varied the injection scenario with different rate of injections. So in the last remark about this is that in all these cases, I kept the normal stress constant. I mean the lithostatic normal stress constant, which means that only for the third fault scenario, you can have variable effective normal stress along the fault. And the last remark is that all these cases were done with approximately the same fault size, which means that I will show you catalogs for kilometer scale fault. So this is the first example obtained with the first scenario, where you have tectonics, you have aseismic slip, but no fluid injection. So on the bottom left diagram, you can see a map view of the fault. So the color scale here corresponds to the critical slip D/C distribution. So somehow it shows you the asperity distribution, the frictional heterogeneity. So the dark blue corresponds to the velocity strengthening region, and all the circles, the colored circles from green to yellow correspond to the asperities. Then you can see also the different earthquakes that we get in this case that are represented with the black circles. So the initiation point of the earthquake is the black cross, and then the extent of the rupture is represented by the circle. So you can see that you have some clusters of events that will rupture asperities, that can also rupture groups of asperities at the same time. And you can also see some smaller ruptures that will only involve a part of an asperity. So you have partial ruptures also of the asperities. So if you can also have a look at the time evolution of the seismicity. So on the top right, you can see the magnitude as a function of time. So the horizontal axis is the time in years, as indicated in the bottom figure. So we can see again that we have clusters, temporal clusters of earthquakes with a magnitude range between 1 and 4 in this case. Then we can also have, as an output of the model, we can also have the average shear stress on the fault, but also the average slip that we can transform into the total seismic moment released by the fault. And we can also, from the seismic activity, derive the seismic fraction of the total moment rising from the fault. So in black here, you have the temporal evolution of the shear stress. In blue, in dashed blue, you have the total moment released by the fault as a function of time. And in solid blue, you see the seismic fraction, so the cumulative seismic moment that is released by the fault. And finally, you can have a look in a different way at the spatial-temporal clustering of the activity by plotting the distance from the fault center as a function of time. So here again, each dot corresponds to one earthquake. And you still see these clusters of earthquakes that activate the fault. And at some point, you can also see that you have some migration. So for instance, here you have an episode of earthquake migration. And this pattern is changing as a function of time during the tectonic loading. So this is a second example where this time,
Pierre,
yeah, yeah,
sorry.
yeah,
In the previous example, in this case, no,
yeah.
the largest magnitude depends on the size of the asperity distribution.
So I will discuss that shortly.
Okay. And the second question is that you have, in this case, you might have a lot of repeaters.
There are repeaters, yes, that's
Yeah.
true. Yeah.
Thank you.
Mm. Yeah, yeah, there are lots of repeaters, of course. Yeah, yeah, yeah. Okay, so this is a second example. This time we have a negligible creep, a seismic slip in between the asperities. So asperity fail in a quasi-locked environment. Um, but still we get approximately the same magnitude range between 1 and 4. We still have some clusters, but maybe the main difference with the last example is that here you can see that you have almost the same number of earthquakes, but over a much longer time period. So before we had 12 years, here you see we have 300 years. And this is related to the fact that we have no aseismic slip. So the stressing rate is different in this case. Now, if you have a look at the way moment is released on the fault, you can see that you have almost no difference between, of course, the total moment and the seismic moment, meaning that reflecting the fact that the aseismic slip is almost negligible. And finally, if you look at the spatial-temporal patterns, still we have some clusters with some episodes of migration. Okay, so we have migration here. Maybe we have some more rapid migration episodes. Um, And now, so the third example is with a fluid injection. So the time period is much shorter. So simply because here we have to add the aseismic slip loading, we have to add also the injection, the overpressure that adds some stressing on the asperity. So in the end, we get a total stressing rate that is much higher than in the previous cases. If you look at the evolution of seismic moment, you recover an important aseismic fraction because there is a huge difference between the total moment and the seismic moment. And if you look at the shear stress evolution, this time you see that the shear stress is decreasing, and this is simply due to the increase of pore pressure that decreases the fault strength. And since you always have a balance between elastic stress and fault strength, this is what is illustrated here. So now if you have a look at the spatiotemporal dynamics of the system, this time we can also plot the evolution of the pore pressure within the fault on top of the earthquake hypocenters. So you can see that still we have some migration, but interestingly, this migration here does not follow the pore pressure fronts. So we don't have the square root migration pattern that is sometimes observed during swarms. So I will come back to this question later. So one important result that has to be mentioned for this kind of system of asperity model is that in some cases, in some situations, it is possible to develop runaway ruptures within the population of asperities, which means that earthquakes are not necessarily confined to velocity weakening asperities, but some ruptures can sometimes propagate through the different asperities and involve the entire fault, including the velocity strengthening parts. And it can be shown that these runaway ruptures generally develop. So if you take dry conditions, okay, they can develop if the asperity density exceeds a critical density that will depend on the strength of the velocity strengthening regions of the fault. In fact, this critical density that allows the development of runaway ruptures is obtained, is the density that makes the spatial average of the A minus B parameter neutral. So it can be viewed as a situation where the average value of the frictional properties are on average velocity weakening. So in our case, we want to avoid the development of such ruptures because the stress release during these ruptures does not obey the same physics as the self-arrested ruptures. So generally, in what I will show you later, we consider just asperity densities that are subcritical, that does not allow the development of runaway ruptures. Okay, so from the different synthetic catalogs that I get in my experiments, so I have a total of 225 earthquake catalogs. We can compute first the magnitude frequency distribution. So this is what is shown here with the colored scale. So this has been obtained for a dry catalog with aseismic slip. So the different colors here correspond to different asperity densities. So different asperity distribution with characterized by different asperity densities. So to make the plot clearer, I just offset vertically the different distributions. And the black lines here simply indicate the power law Gutenberg-Richter decay. So the range of power law decay that we obtain here. So we get here in this kind of models, we get a nice power law decay between two magnitudes. We have between a completeness magnitude that is of the order of 2. So I have to say here that the completeness magnitude is not related to observational constraint, but it's the physical completeness that we have in our catalog. This is just the limit, the smallest earthquake size that we can generate in the model. So which is mainly controlled by the resolution that we are able to achieve in the simulation. So this is the lower magnitude that is represented by the star, and we have a maximum magnitude that increases with the asperity density. And in between these two magnitudes, we have a nice power law decay that we can characterize with the B value. Okay, we can.
Pierre,
Yeah,
sorry, I have a question.
yeah.
Can you clarify in your model how much the asperity density correspond to the largest side of the asperity? Because you might have the same density with different sides, because otherwise, to me, it's difficult to interpret the previous picture.
You mean the same asperity density with a different distribution of patches, right?
Yeah, or if you can normalize the distribution, the asperity density to the largest sides of the asperity.
Yeah, so definitely this is something that has to be done. So I will show you some results
Okay, thanks.
about this, but for sure this will be incomplete and it will have to I mean we cannot I mean for the moment I don't understand everything this kind of simulation, so this is an important question, of course.
Yeah, no, thank you, thank you.
I'm sorry to interrupt as well. Is it just the B value that you see, or do you actually also see a change in the shape of the functional form, like a tapering, let's say?
Oh, that's so I've not been so far, but that's true that there might be also change in the I mean in the shape of the magnitude frequency distribution. Yes, yeah, yeah.
Okay.
So the for instance if you compare the red part and I mean the red curve by high density and the blue one, there can be a change in shape, but this can also be related to the way asperities are distributed on the fault plane.
Okay.
But I mean, I have no clear answer about that. Um, Okay, so we can in addition to the magnitude statistics, we can also look at the temporal clustering. And one way to look at this temporal clustering is to look at the distribution of interevent time delays between, so the time delays between successive earthquakes. And yeah, and in our case, we can see that this distribution. So here, what I'm showing is the distribution of time delays, interevent time delays, normalized by the mean interevent time delay within each catalog. So this distribution generally follows or is close to gamma law distribution, as suggested previously for natural sequences. And so this distribution at early time, in fact, the distribution follows a power law decay that can be characterized by an exponent that is defined as the parameter gamma minus 1. So at early time, we have two different n members. We have if the gamma parameter is 0, in fact, we have an inverse decay that corresponds to a high degree of clustering. And in the case where the decay is almost negligible, the distribution, in fact, fits an exponential law that corresponds to Poissonian seismicity. So this gamma parameter is a way, in fact, to quantify the degree of temporal clustering that we have in the catalogs. Then, if we want to look at the spatiotemporal behavior of the catalogs, we can look at the distribution of migration speed. So here, what I define as a migration speed, it's related to the distribution of interevent of the ratio between successive interevent distance divided by the interevent time. So in the catalogs, we see that we have some kind of a Gaussian distribution. And what I will define as the migration for one catalog is simply the mean of this distribution. And we can also estimate some standard deviation represented by the horizontal bar here. Okay, so the different triangles here give you the mean of each distribution with the standard deviation. So here again, we have a change in this behavior for different asperity densities. And finally, so there is another metric we can compute for these catalogs. It's the effective stress drop. So the effective stress drop is simply defined as the total seismic moment released by an earthquake cluster divided by the typical size of the earthquake cluster. So here you can see the evolution of this quantity as a function of earthquake cluster size. So you see that it's something that is changing through the whole earthquake sequence. But the idea here is that we compute the effective stress drop as the stress drop when the first earthquake cluster reaches the fault boundaries. Okay, so let's have a look at the mechanical control on these different parameters. So if I look at the magnitude frequency distribution, we clearly see here for all the different catalogs that I have that the B value is decreasing with the asperity density. So we have this very first order scaling that appears irrespective of the fault scenario that we can consider. So here in this diagram, the locked fault scenarios are represented with the red symbols, the aseismic dry scenarios with the green symbols, and all the injected faults scenarios are represented with the blue symbols. So to the first order, we have this decrease, and we also have some huge scatter, and we cannot from this scaling distinguish between a locked fault environment, a creeping fault environment, or injection environment. So to better understand what controls this change in B value, we can have a look at the maximum magnitude in each catalog. And here, the maximum magnitude appears to be largely controlled by the size of the maximum asperity that we have on the fault. Okay, so the scaling is quite good for many earthquake sequences. So here, so it's not only in fact the size of the maximum asperity; it's also related to the stress, the shear stress prevailing on the asperity, the initial shear stress prevailing on the asperity. So we can see that the scaling is given by this equation here, where A asp is the size of the maximum asperity, and delta tau VW is the stress drop that we expect to have on the asperities, and that is related to the initial stress tau A minus the residual stress during dynamic sleep. So this scaling works well for many simulations, but we still have some deviation there that corresponds, in fact, to system size rupture, runaway ruptures, that even with subcritical asperities, we were not able to control in this case. So if we consider this change of maximum magnitude with asperity size, we can conclude, well, the maximum size of asperities is controlled also by the asperity density, and if we simply relate these two parameters, we can expect some scaling for the B value change, that has this form here. So we have a log inverse log dependence on the asperity density with rho null here, that is the minimum asperity density given by the smallest asperity on the fault. So we can see that this scaling representing in black can explain part of the b-value evolution. I mean, can explain the first order of b-value evolution with asperity density on the fault. But still we have some scatter, and this scatter can have different origins. So to have more insight into this scatter, we can have a look at this group of blue triangles that you have here. So this corresponds to an experiment where the size of the asperity density is the same, but we have changed the stress, the initial stress and the asperity for each simulation. And you can see that almost all the variability that we can see can be explained by the stress conditions prevailing on the asperity. Okay, so I will skip this. Concerning temporal clustering, if I look at the gamma parameter of the gamma distribution, here again, I get similar results where the gamma parameter is decreasing with the asperity density, which somehow, like for the b-value, makes sense because with higher density, you expect to make stress transfers between the asperity stronger, and thus to promote more clustering within the catalogs. Okay, so this is reflected by the fact that the gamma value is decreasing here with the asperity density. And here again, there is no real distinction between earthquake sequences driven by fluids, by aseismic slip, or occurring within locked condition. So I will come back later to this gamma parameter, but to better understand what happens, we can also have a look at the migration speeds. And here again, like for the b-value, like for the gamma parameter, we see that we have a dependence on the asperity density. So generally, this migration speed, this earthquake migration speed, tends to increase with the asperity density. But contrary to the previous cases, you have a clear distinct behavior depending on the fault scenario that you consider. So generally, migration speeds are much smaller when you consider locked fault environments and will increase with the addition of aseismic slip and with the addition of also injection within the system. So we from this representation, we can see that this migration speeds has something to do with the stressing rate which is experienced by the asperities, and that is controlled by the aseismic slip on the fault. So to illustrate this, let's have a look at what happens during two successive earthquakes on the fault. So here you have a picture of the fault surface. The color here represents the stress change between before the first earthquake, from the first earthquake, sorry, from the outset of the first earthquake. So here you can see that the first earthquake is causing the failure of this asperity. You have a stress release here and a stress concentration at the edge of the asperity. Then this first earthquake is followed by a second earthquake that will release stress on this asperity here. And in between, you can see that the stress concentration is moving from the first asperity to the second one, like this, okay? And this stress concentration corresponds to an aseismic slip front, a post-seismic slip front that propagates from one asperity to another. So one way to interpret the migration speed is to say that this migration speed seen from the earthquake catalog results from a creep front that propagates from one asperity to another. So we can
Pierre,
yes.
sorry again for the clarification.
Yeah.
Therefore, you might have a composite main shock, where it rupture more than a single asperity.
Yes,
This is what you define runaway, correct?
Well, it depends. The runaway is in case you have a rupture that propagates through all the fault. Okay, so it's not simply a rupture that propagates from one asperity to the second one, then stops. Okay, runaway means that it propagates on the whole fault. But if you don't have any runaway rupture, you can still have self-arrested ruptures that will involve maybe two asperities or three asperities that are close enough to each other within the fault plane.
Okay, thank you.
Yeah. But this
Yeah.
is here what I illustrate is a bit different because this is not one rupture that involves two asperities. These are two successive ruptures that are that interact simply by an aseismic slip front that is not seismic, in fact.
Yeah, I have a question related to that. Sorry.
Yeah.
You don't see an evolution in the B value
I don't see an evolution of the B value
during a run. So during the slip evolution, right?
Oh.
It's only for different asperity densities that you see that. Or how do I read this? What you showed? It's so the typical decrease in B value that you would observe with slip, let's say in experiments, you don't see.
You mean if you look at the temporal evolution of
Yeah, temporal or slip evolution.
Yeah, so here in these catalogs, I think I don't have enough events to look at the temporal evolution of the B value. So what I'm
Okay.
showing is simply a comparison between different catalogs, and I compute one B value for one catalog.
Okay.
With one B value. But
Thanks for clarifying. Yeah.
sorry.
And sorry, I have one clarification as well
Yeah.
based on Massimo's comment. And would you say it's fair then for what you're defining a runaway rupture as something that is limited in the maximum magnitude, essentially like that plot that you had there before where one of the lines was going above it?
Yeah, exactly. Because so if you look at this,
Yeah, that one.
yeah, typically the fault size is about here. So I don't have any ruptures that are larger than this one, and these are correspond to runaway ruptures. Yeah,
Okay.
yeah. Okay, so one way of interpreting these migration speeds between earthquakes is to say that this is related to aseismic creep fronts that propagates from one asperity to another. Now, if you have this idea in mind, you can compare the migration speed seen from the earthquake statistics with the creep rate that is occurring on the fault. Why? Because from a simple fracture mechanics argument, we expect that this aseismic slip front, the speed of this slip front has to be related to the slip rate occurring, the aseismic slip rate. And this is something that we can measure and that we can measure in the model. So here I show you a comparison between the migration speed observed from earthquake catalogs and the creep rate that occurs in the velocity strengthening part in between the asperities. And we see, so this creep rate is defined as V sub C, and here it's normalized by VP, which is the far-field tectonic rate that we applied on the boundaries. And we can see that here we have a nice scaling between the migration speed and this creep rate, okay, meaning that that part of the migration speeds can simply be explained by the loading condition that we have in between the asperities. So now if we come back to this asperity density dependence, we can extend the scaling that we have and accounting for the fact that under higher asperity density, the stress redistribution within the asperities, because of the direct effect of the friction law, tends to increase this creep rate and give rise to an exponential dependence with asperity density on the creep rate. And this way, we end up with a scaling of this form where the migration speed is controlled by an average creep rate V sub c to the power 1/2 multiplied by an exponential dependence on the asperity density. And this scaling, represented in black, explains quite well what we observe in the different catalogs. So now, at this point, we have three different statistical features: the b-value, the gamma parameter, and the migration speeds that all depend on asperity density. So if we look at this and say, well, is it something that is useful to say something about fault process at depth? The answer is probably not, because we don't have any idea of what is the asperity density on real faults. However, if we couple all these different scalings, we can replace the asperity density by one of this metric, by one of these parameters. And we get something that is much more interesting, is that we have some scalings between, for instance, the b-value and the migration speeds of earthquakes, or between the gamma parameter and the migration speeds of earthquakes, of earthquake interaction. And in this case, the nice feature is that we have distinct scaling between the different fault scenarios that we have. So if you look at the b-value or the gamma law parameter, all generally and this simply arises from the fact that the migration speed is different in the different fault environment. So this is something that becomes much more interesting when we want to apply this to real conditions. So I will skip this because we are running late. Another nice outcome from these different scalings with asperity density is that within the synthetic catalog, we get linear scaling between the b-value and the gamma parameter of the gamma law. But here again, we don't have any distinct feature between the different fault scenarios. Okay, so if we come back to the real observations and try to make some comparisons with what happened in the synthetic catalogs, we know from real observations that the migration speeds of earthquakes tends to decrease with the duration of earthquake swarms. If I compare this to what I have in the models, I can see that the migration speed, so if I reverse the scaling, I can see that the migration speed is decreasing with an increasing value of the gamma parameter, which means that somehow with less clustering, I have smaller migration speeds, which somehow means that when the earthquake clusters are longer, I have smaller migration speeds. So it has some connection with, it probably has some connection with the scaling with duration that is observed. Also, what I can see is that the migration speeds that are obtained in the models are well within the range of what is observed for real sequences. So in this diagram, for instance, I reported the real swarm data that are provided in the paper of Dublanchet on top of the numerical simulations, which shows that we have this correct range of migration speeds. However, we are still not able to explain the largest value of the gamma law that are sometimes observed. Okay. So to go further into the comparison with real data, it is necessary to use the same definition of earthquake migration, which in the case of the natural swarms is defined from the distribution of interval distance and interval time delays. So to do that, I would need to decluster the synthetic catalogs and work at the cluster level, just like in the real swarms. Concerning the b-value, we see that we have a decrease of the b-value for a given fault scenario. We have a decrease of the big value with the migration speed of earthquakes, and this is essentially related also to the creep rate experience in between the asperities. However, this is probably not consistent with some observations because as the b-value decreases with increasing migration speeds, this means that the b-value is decreasing with increasing creep rate on the fault. So the b-value decreases with stressing rate experienced by the asperities. And this feature is in contradiction with what is observed in reservoirs, where the b-value, on the contrary, increases with the stressing rate. However, the probable explanation for that is that we have also to account for the asperity distribution, but also for the stress prevailing on the asperities to account for the full range of observations about the b-values. And finally, I will just mention very bad news is that in this kind of models, there is no scaling, there is no clear scaling between the maximum magnitude of earthquakes and the injected volume if we look at the fault scenario 3. So here, this is illustrated in the last diagram here that I show. You have the maximum magnitude as a function of injected volume. So all the dots correspond to the numerical results. And the dashed lines that you can see are the scalings of Maggar in black and from the paper of Gallis in 2017. So you can see that here all the experiments the 5 injection experiments are shown in this diagram, and there is no clear scaling with injected with a volume. And it's this has to be related to the fact that the maximum magnitude, in fact, in such models is entirely related to the size of the maximum asperity that we have on the fault. So from this property, then the question of what is the volume necessary to trigger the failure of the largest asperity is essentially a matter of nucleation. And you can see that for a given earthquake magnitude, depending on the nucleation process, you can have the same magnitude for a wide range of different volumes. So if you look, for instance, at this line, you can see that this magnitude can be triggered for 3 orders of magnitudes of injected volumes. So somehow the set of points that I see here correspond to, in the real observation diagram, to the reservoir scale. So this approximately corresponds to the range of volumes that you can see in this part of the diagram. So in a way, this might explain the scatter in the best case, this might explain the scatter that we observe in this kind of scaling. Okay, so now I will conclude. So we have now huge high-resolution catalogs, and we want to use earthquake statistics to quantify aseismic slip, stress, and fluid depth. So what I can show from the models is that the earthquake statistics essentially reveals the amount of creep or aseismic slip that we have on faults. But unfortunately, it seems to be less sensitive to the overpressure or to the fluid volumes that we inject within the fault. So there is, the good news is that this might be useful to infer aseismic slip, but for the hydrological part, this is not so clear. However, all the results presented here would need to be refined, especially by analyzing the synthetic clusters at a much smaller scale, at the scale of the individual swarms, which requires to decluster the catalogs. And finally, of course, this analysis should be extended to maybe more complex models that incorporate the roughness, that incorporate more elaborate pore-elastic couplings to have the whole range of triggering mechanism that we expect within the fault systems. So to conclude, I will just say that all the results here were, all the catalogs were obtained with the code Cyclops, which is entirely available on GitHub. So with the documentation, so this can be reproduced, and all the catalogs are also will be shortly made available with all all the earthquake catalogs and also all the sleep histories on fault. So thank you for your attention. I think I've maybe a bit long, but I will be happy to take a question now.
Pierre, that was great. Thank you so much. I will invite people to join me on mute if you'd like to. Give Pierre just a minute to catch his breath, have a drink, and get ready to lead the discussion. But you already had a nice discussion from several people. Okay,